pause the video and carefully try this problem. Well, now that I hope that you've given that a shot, let's go through this. Of course, I hope that you tried to solve the problem carefully using the techniques that we've been talking about in this video series and in my previous video series. So first of all, we have to choose a problem-solving framework. And our first two frameworks to choose from in the class are kinematics and Newton's second law. We look at the concepts in the question to see what framework to use. The problem mentions mass of kilograms, which fits into Newton's second law. And friction force also fits into Newton's second law. On the other hand, there's also this concept of height, which does not fit into Newton's second law, but would be a good fit perhaps for kinematics, because height is a type of distance, and kinematics is a way to think about distances. The problem also asks, how long does something take? Well, kinematics framework, again, is a good framework for figuring out how long a motion takes. So we have concepts from both kinematics and Newton's second law. So we're going to use both the kinematics framework and the Newton's second law framework for this problem. Not projectile motion. We're not using projectile motion because projectile motion would be if the only force on the object was the force of the Earth's gravity. And in this case, there's a number of other forces on the object besides the Earth's gravity. So what do we call it when it's not projectile motion? The other type of kinematics is what we could call general kinematics. And this will be general one-dimensional, because the object is moving in a straight line. Since the object is moving in a straight line, we can treat that as one-dimensional kinematics. What's the link between kinematics and Newton's second law? The link is acceleration, because the concept of acceleration appears in both the Newton's second law equations and the kinematics equations. But we want to think in terms of components. So are these going to be linked by ax or ay? Well, we can anticipate what our axes will be for this problem. Well, remember that we'd like to choose an axis that points in the direction of motion. And the direction of motion in this problem will be down the inclined plane. So I'm going to choose an x-axis that's down the inclined plane, and then a y-axis perpendicular to that. And therefore, we can see the motion will be in the x component. So we expect that these are going to be linked by a sub x. Maybe we're going to use kinematics to figure out a sub x and then substitute that into Newton's second law. Or maybe we're going to use Newton's second law to figure out a sub x and then substitute that into kinematics. We'll have to see as we proceed with the problem. But this is our plan. Our plan is to use both these frameworks as linked up by a sub x. Okay, so let's make sure we have our sketch of the problem. We already were given a sketch. We can include the velocity vector in this sketch. The direction of the velocity indicates the object's direction of motion, and the object is sliding down the inclined plane, so our velocity vector will point down the inclined plane. Also, in terms of kinematics, let's identify the key points in time in this problem. So the object is going to begin at this point. We can call that point in time, we can say that that represents t sub 0, which we can call 0 seconds. And it seems like the other key point in time we care about is when we reach the bottom of the ramp, and we'll call that t sub 1. The question is asking how long it takes to go from the top of the ramp to the bottom of the ramp, and that's an indication that those are the two key points in time in this problem. So the path of the object's movement will be this diagonal line. This diagonal line becomes the path of the object's motion. Let's identify the question with a question mark and a symbol. The question is asking how long it takes to reach the bottom of the ramp. This is a question that I think that we can build into the sketch. So we want to know how long it takes to go from this height to this height, and we can build that into the sketch. Now, what's the best symbol for that? We indicate the question with a question mark. Well, the symbol for how long something takes is delta t. The symbol for the amount of time that elapses between these two key points in time is delta t. We want to know how much time is elapsing between these 2 points in time. That symbol is delta t, so we'll label that with a symbol and a question mark. And notice that by building this into the sketch, we can make clear that this is the delta t between when the box is in this position and when the box is in this position. So when possible, build information and the question into your sketch. Check that the units are SI units. Kilograms is SI units. Meters is SI units. This problem is numeric, not symbolic, so we can skip this step. Identify the object that we're applying Newton's second law to. Well, since the problem mentions the mass of the box, we're probably going to use the box as the object, and we're going to be applying Newton's second law during the interval between time 0 and time 1. That is, during the interval between when it starts sliding down the ramp and the time when it reaches the bottom of the ramp. So the object is going to be the box, and we're going to use Newton's second law during the interval that it begins sliding down the ramp and then reaches the bottom of the ramp. Start your free body diagram. Start the free body diagram by drawing a vector for the object's weight. Make sure that you label that accurately. And remember, there's a simple rule for the direction of the weight. The direction of the weight is always down. It doesn't matter whether you're doing an inclined plane problem or a horizontal floor problem. The direction of the weight is always down. So we drew that. And now moving on to the next step, we want to ask what is touching. What is touching the object? And the only thing touching this object is the ramp. The ramp is a surface, so it will exert a normal force. And there's a simple rule for the direction of the normal force. The direction of the normal force is perpendicular to and away from the surface of this ramp. In order to show that, I'll have to draw in a 35-degree reference line here so we can get the correct angles. Okay, so we drew in the necessary reference lines. Here's the normal force vector perpendicular to and away from the surface of the ramp. And we need to label that with the correct symbol. Remember, we're using dashed lines here to show that this is not a line that represents a force. It's just a reference line. The solid lines in our free body diagram will be our force vectors. Now, remember, we have to get into this habit that whenever there's a normal force, there's always the potential for a frictional force. And in fact, we know there is friction in this problem, so now we have to add the frictional force also from the ramp. And there's a simple rule for the direction of friction. Is this kinetic friction or static friction? Well, this object is sliding down the ramp. Since it is sliding, that's when we apply kinetic rather than static friction. And the simple rule for the direction of kinetic friction is that it's parallel to the surface and opposite to the direction of sliding. So since the object will be sliding down the ramp, the kinetic friction will point parallel to and up the ramp, and we need to add that to our free body diagram. Here's that vector pointing parallel to and up the inclined plane, and we need to label that. Well, that's the force of kinetic friction. Try to use the exact right symbol. So that's this force vector, the force vector from the kinetic friction. So now we've completed this free body diagram. Is there anything else touching the object besides the ramp? No, so there's no other forces on the object. We complete the free body diagram simply by noticing what is touching the object. Don't overthink it, but remember, anytime there's a normal force, we also have to consider whether there could be a frictional force from that same surface. Now we're ready for our force table. I think we already picked our axes, so now we start the force table. And we'll start that force table by thinking about the magnitude of the object's weight. There's a special formula for the magnitude of the object's weight. So write down that special formula, W equals mg, and then we can try to plug in. The mass is 8 kilograms. Little g is 9.8 meters per second squared. 8 times 9.8. So we'll get 78.4 for the magnitude of the weight. Remember that when we've solved this equation, we need to put in units, and the units for the weight force are newtons. Now we can add that down here to our force table. The weight is 78.4 newtons in magnitude, and now we have to start thinking about the x and y components of the weight. Now, don't do that on autopilot. Notice that the weight here is neither parallel nor anti-parallel to either of these axes. The weight is at an angle to both of these axes, and therefore we're going to have to draw a right triangle to break the weight force into components. We didn't have to do that, I think, for the last few problems. The last few problems, we didn't need a right triangle to break the weight into components because we were using horizontal and vertical axes. But here we're using diagonal axes, and now we're going to need the right triangle method to break that weight into components. Remember, don't mess up your main free body diagram to do that. We'll do that in a separate sketch. Through the tail of the overall vector, I'm going to draw a line parallel to the x-axis. And now through the head of the overall vector, I'm going, so that's this line here. Here's the line that's parallel to the x-axis, overlapping with the reference line. And through the head of the overall vector, I'm going to draw a line that's parallel to the y-axis. So here's that line parallel to the y-axis. Here's the line parallel to the x-axis. Now we have that right triangle that we were going for. So I can just clean that picture up. I can say that now I want to figure out the arrows on these two lines. We can say that using this rule, where we have the head of the overall vector, we should also have the head of the component. And where we have the tail of the overall vector, we should have the tail of the component. Make sure you label those. This was the side parallel to the x-axis, so this is w sub x. And this was the side parallel to the y-axis, so this is w sub y. So those are our components. Remember, you need to resist the temptation to draw the right triangle like this. We don't want to draw a right triangle with horizontal and vertical legs because the legs are supposed to be parallel to our axes, and our axes are not horizontal and vertical for this problem. Now we should figure out the signs on these components before we figure out the magnitudes. Wx is pointing in our positive x direction, and Wy is pointing in our negative y direction. We can say that this side is the hypotenuse. Why is this the hypotenuse? Because it's opposite from the 90-degree angle. And I guess before we can do anything else, we have to figure out some of these little angles inside this triangle. We need to do geometry. We know this angle, but we need to know some angles inside the triangle. Well, the trick for that is to use geometry. We extend this vertical line down, and we extend this horizontal line across, and now we have a large right triangle. A large right triangle. So we know that this angle plus this angle adds up to 90, so this angle must be 90 minus 35. This will be 90 minus 35, which you could calculate on your calculator or by hand, is 55 degrees. The acute angles of this large right triangle should add up to 90 degrees. So this angle must be 90 minus 35, which is 55. And I'll go ahead now and figure out this angle. Well, this angle plus this angle should again add up to 90 because they're the acute angles of a right triangle. So again, this angle is 35 degrees. So that the acute angles of this small right triangle add up to 90. And we're going to focus on this angle of 35 degrees for using SOHCAHTOA. It would be legal to focus on the 55, but it's more conventional to focus on the 35 since that's the number we were given in the problem. So if I focus on this angle, that means that this side is adjacent. Adjacent to who? Adjacent to the 35 degrees that we're focusing on. And this side is opposite to the 35 degrees that we're focusing on. We can't figure out who's opposite and who's adjacent until we find the angles inside here and decide which angle we're focusing on. Now we're ready for SOHCAHTOA. The sine of 35 degrees is opposite over hypotenuse. cosine of 35 degrees is adjacent over hypotenuse. The length of the opposite side here is the magnitude of Wx. The hypotenuse here, well, we should fill in the hypotenuse now because we know a number for that. So let's change this symbol to W, because now I'm just going to write down the magnitude of that weight. We already figured that out. We already figured out that the magnitude of the overall weight is 78.4. The magnitude of the overall weight is 78.4 newtons. Notice that whenever you write a number in physics by itself, you should always include the units. But when you substitute a number into an equation, it might be better to leave the units out to keep the math simpler. But whenever you write numbers in physics by themselves, always include the units. Adjacent here is the magnitude of W sub y. Hypotenuse is 78.4. As usual, we've talked about how in SOHCAHTOA you should focus on the magnitudes of the components, not on the assigned values, because we're trying to represent lengths, and lengths can never be negative. So to ensure that these are not negative, we use absolute value signs. Now we'll solve by multiplying both sides by 78.4. In both equations. And we're ready to figure out the magnitudes of the two components using our calculator. 78.4 times sine 35. Make sure that you're still in degrees mode. 78.4 times cosine 35 degrees. All right, I guess I'll round this up. Let's see, this digit is a 6, so I'll round this digit up. And when you round this digit up, this becomes a 0, and we carry over the 1. So this rounds up really to, I guess, 45. Do you know how to do that rounding? So this will be 45.0, and we put in the units of newtons. This digit makes this digit get bigger, and that brings us all the way up to 45. And then W sub y here I'll call 64.2 newtons. That's the magnitude of W sub y. All right, now remember, these absolute value symbols here are supposed to remind us that the SOHCAHTOA equations only tell us the magnitudes of the components, not the complete components. These are the symbols for the complete components, including plus or minus signs. And as we already determined, W sub x should be positive. But W sub y should be negative. We figured that out before. W sub y is negative. If we leave out this negative sign, we'll get the problem wrong. And notice the SOHCAHTOA equations don't tell us that W sub y is negative. That's why we're using absolute value signs here, to remind ourselves that this SOHCAHTOA equation will not tell us whether W sub y is negative. We have to figure that out in a separate step. We have to include this negative sign when we plug into Newton's second law, or we will get the wrong answer. Okay, so we succeeded in breaking this into components. So you've probably noticed that whenever I break vectors into components, I try to show all the steps. Because remember, we want to avoid being on autopilot. We need to understand the principles and the process for breaking things into components so that we can adapt when the problems get a little bit different. Now, obviously, once you really get the hang of these problems, it's okay if you start to notice that there's certain commonalities in problems and you feel that you can skip some of these steps and not write all of these steps down. That's okay, but it's important that you always be able to write down all these steps as necessary. Don't just try to memorize some trick that will give you the correct components. Make sure that you understand the process for figuring out the correct components, so when the problems change a little, you'll be able to change your process. So again, it's okay to skip some of these steps or do some of these steps in your head if you're starting to find this to be easy, but make sure that you could do all the steps on paper. And then if you see a problem that's a little different from what you've seen before, make sure that you really do all the steps on paper so that you can adapt to that situation. Okay, so here we have Wx is 45 newtons. And our W sub y was negative 64.2 newtons. We should put a plus sign in front of this positive component, which will help us to remember the negative sign that we need in front of the negative component. Okay, so we broke that weight force into components. We also have to deal with the normal force. Now there's no special formula for the magnitude of the normal force, so I'm just going to represent this by the symbol, little n, because we don't know the value for that, and now we have to figure out n sub x and n sub y. The normal force here is parallel to our y-axis, so the x component is 0. And since the normal force is pointing in the positive y direction, n sub y is positive. And again, because this component is 0, the entire magnitude goes into the y component. Well, it was certainly a lot easier to break that force into components than to break the weight. It's easier to break the normal force into components here because the normal force is parallel to one of the axes. It's more difficult to break the weight into components because the weight is not parallel or anti-parallel to either axis. When you have a force that's at an angle to both axes, you need to draw a right triangle to break it into components, like the weight. But when you have a force that's parallel or anti-parallel to an axis, like the normal force, you do not need the right triangle method to break it into components. We didn't have to draw a right triangle to break this normal force into components. Now moving on, we have to deal with the kinetic friction. We have a special formula for that. Remember, write the general formula before you plug in. Is there anything we can plug in here? Let's see, yeah, we know the coefficient of kinetic friction is 0.3, so I can plug that in. It's very important to be willing to go back and keep going back to reread the problem. Be willing to keep going back to reread the problem to see if there's any numbers that we need. So we got back that number of 0.3, but we don't know yet the value of the normal force, so I'll continue to represent that by the symbol little n. Write the general formula first, then plug in, and then when you have your expression, we can plug that in over here. Remember, keep your force table neat and do your extra work off to the side. Keep your force table neat because this is our way of organizing our work. We have a mathematical expression here for the kinetic friction that involves one number and one symbol. I hope that doesn't weird you out. There's nothing bad about having a mathematical expression with one number and one symbol. We'll be able to use that mathematical expression perfectly fine to break this into components. This force of friction is parallel, anti-parallel actually, to the x-axis, so the y component is 0. Again, frictional force is pointing in the negative x direction, and because this component is 0, the x component magnitude is the same as the overall magnitude. So that's another force that's easy to break into components. By the way, remember, this does not stand for newtons. This is not n for newtons. That would be a capital N. It's lowercase n for normal force, so we have to keep writing that. Now I think we're done with the force table. Make sure that your force table includes all the forces from your free body diagram, and notice how nice and clean and neat we've kept both of those pictures. That's important for these types of problems, so try to build that habit. All right, so we've completed these steps, making sure to include a plus or minus sign in front of each non-zero component. By including this plus sign in front of this positive component, we're more likely to remember the negative signs we need in front of the negative components. If we leave out, say, this negative, we're going to get the problem wrong. So make sure that you're including that negative sign. Our next step is moving on to the Newton's second law phase to write out the Newton's second law equations at the top of two adjacent columns. Here are our general Newton's second law equations. Now we can start plugging in. The sigma symbol means to add all the x components of the forces in this equation. Similarly, this sigma tells us to add all the y components of the forces for this equation. Continuing to plug in, we should plug in values for each of the components from our force table. W sub x is 45 newtons, n sub x is 0, f sub kx is negative 0.3 n, w sub y is negative 64.2, n sub y is n, f sub ky is 0. Now we can plug into the right side of our equation. We need to plug in for the mass. The problem says we have an 8 kilogram box, and we should know that kilograms are the units that indicate mass. So we plug in 8 kilograms for the mass in both equations. Now we deal with a sub x and a sub y. We know that the object is moving parallel to the inclined plane. That is, the object is moving in the x component. We know that there is no motion perpendicular to the inclined plane, so we know that there is no motion in the y component. Since the object is motionless in the y component, we know that a sub y is 0. On the other hand, we have no information about a sub x. So we continue to use the symbol a sub x. Now we can simplify these equations. We take advantage of the zeros to simplify these equations. So now we've carried out this step. We used the idea that the object is motionless in the y component to say that the y component of the acceleration is 0. Now we are not going to move on to this step yet. We're not going to use algebra for Newton's second law yet. Instead, as we've seen, this is a good time to pause and start working on the kinematics framework for this problem. Here's our kinematics handout. As we've discussed in previous videos, we have to decide what type of kinematics we're going to be applying. There's a simple type of kinematics involving constant velocity, and then there's the more common type of kinematics that involves constant acceleration with changing velocity. So first of all, we have to decide, is the velocity on this problem constant, or is the velocity changing? You might want to pause the video and ask yourself, how can you tell whether the velocity is constant or changing on this problem? That should have been really easy to work out because the object in this case starts sliding down the ramp. The way this problem is worded implies that the box starts sliding from rest. I know they didn't quite put it in so many words, but that's what this wording is supposed to imply. But they imply that when they say that it starts sliding. When they say that it starts sliding, they're implying that before that it wasn't sliding, i.e. it was at rest. So this type of wording should be read to imply that the object starts sliding down the ramp from rest. But doesn't that mean that its velocity must be changing? From the wording of the problem, we know that the box starts from rest and then begins sliding. But that means that the speed increases. The speed increases from 0. Originally, the speed was 0 when the box was at rest, and then the speed increased as the box began sliding. But the speed, remember, is the magnitude of the velocity vector. So if the speed increases, that means that the magnitude of the velocity is increasing. And if the magnitude of the velocity increases, that tells us that the velocity is changing. So we know this is a problem with changing velocity, not constant velocity. So hopefully it's going to be a problem with constant acceleration. Let's make sure this is a problem with constant acceleration. We already know it has changing velocity. And remember that the acceleration is determined by the forces. Acceleration is determined by forces, as we discussed in the previous videos. So if the forces are constant, then the acceleration will be constant. Well, here's the forces on the object in our free body diagram and our force table. And there's no reason to think that any of these forces are changing over time. The weight is certainly going to be constant over time with these numerical values. And the normal force and the frictional force will have values that are set by the weight force. If the weight force isn't changing, there's no reason for the normal force and the frictional force, which are influenced by the weight force, to be changing. So we can say that it looks like all these forces will be constant. And if the forces are constant, that means the acceleration is constant. Because the forces in this problem are constant, the net force will be constant. And since the net force is constant, the acceleration is constant. The acceleration is determined by the net force. So we've decided that this is a problem with constant acceleration and changing velocity. Okay, so we've decided we're going to use the kinematics framework with constant acceleration and changing velocity. That's the typical type of kinematics, most typical in physics classes. We used this idea that acceleration is constant when the net force on the object is constant. We've already decided that the object that we are applying the kinematics and Newton's second law equations to is the box. During the interval of time after it begins sliding down the inclined plane until it reaches the bottom of the inclined plane. The interval of time is the interval between time 0 and time 1, between when it begins sliding from the top of the inclined plane and when it reaches the bottom of the inclined plane. We've already seen that the units are SI units, and therefore the units are consistent. The step's not relevant. We've already been working on our sketch. The sketch already has this distance information that was already built in to the sketch. We've already went ahead and wrote down the key points in time, and we already set time 0 equal to 0. That was convenient to do earlier. I don't think there was any other time information that we can build into the sketch. Well, we built the question about the time. The question was asking about the time, and we built that into the sketch. We've seen in previous videos that this is also a good step for building the velocity information into our sketch. So let's do that. Well, remember we already noticed that this object is starting its slide from rest. When the problem says that the box starts sliding down the ramp, that implies that it starts sliding from rest. And that tells us that the initial velocity at the top of the ramp was 0. So let's build that into our sketch. I've built that into the sketch. The object is starting to slide from rest, so its initial speed is 0. But the speed is the magnitude of the velocity, so the initial velocity is 0. Now I'm focusing here on the x component of the velocity because the object is moving in the x component. The object is moving parallel to the inclined plane, which is our x direction. So for kinematics, we're going to focus on the x component. We don't have any particular information so far about the velocity when we reach the bottom of the incline, so there's nothing to write down about this velocity yet. Already wrote down our axes. Again, we already built that question into the sketch. Remember that for kinematics problems, it's really important to label the initial and final positions on the path. So we'll say this point is the initial and this point is the final, and we should actually write down the letters I and F to label those on our sketch. Always actually write down the letters I and F to label the initial and final points when you're doing kinematics. That'll be more and more helpful as the problems become more difficult. Remember that the initial and final point are the 2 points that we're going to plug into our kinematics equations. These are good points to plug into the kinematics equation for one thing, because the question is asking for the time that elapses between those 2 points. So make sure you actually write down the I and the F in your sketch to label the initial and final positions. That's something that we don't have to do just for a Newton's second law problem, but we do have to apply that for a kinematics problem, because the kinematics equation involve both the initial point and the final point. So now we've completed our preliminary steps for kinematics. We've completed now the preliminary steps for kinematics. So remember, here's how we set up the mathematical approach for kinematics. Remember, we're using this right-hand column because we're doing a problem that involves constant acceleration with changing velocity. We're going to write down the setup. Remember that on this problem, we're applying kinematics to the x component because the object is moving in the x component. So our setup is to write down these 5 kinematics variables for the x component. And we should actually write those down on our paper. This is a crucial step. Remember, the kinematics framework is not an equation, it's a listing of variables. So here's our kinematics framework, listing the 5 key kinematics variables. Delta t, delta x, v initial x, v final x, and a sub x. So this is the framework we're going to use in 3 side-by-side columns to keep our mathematics as neat and clean as possible. So we've completed this step. Now we can go back and start plugging in. Because we're doing Newton's second law and kinematics, we're going to have a 3-column approach. Remember, we only have to apply kinematics to the x component because the object is only moving in the x component. But we have to apply Newton's second law to both the x and the y component because there are forces that exist in both the x and the y components. So let's plug in some specific numbers and symbols into the setup for our kinematics approach. Let's see, so for our delta t, we don't know that. And here's an interesting one, delta x. So do you see delta x in this picture? It would be useful to build delta x into this picture. How would we build delta x into that picture? Well, do you see delta x is going to be this distance. The object is being displaced from here to here. The object is being displaced from here to here. So this distance will be delta x. This distance here will represent delta x. Object starts here and is displaced down to here. Delta x is defined in terms of initial and final points. This point is our initial point for the beginning of the displacement. And this point is our final point for the end of the displacement. Those are good initial and final points because the question is asking about the time that elapses between those two. So the object is being displaced from this initial point to this final point. So we can see off the bat that the displacement will be positive. We're starting over here and being displaced in our positive x direction. So we can go ahead and say that the displacement will be positive. Remember that this stands for a component. This symbol stands for the x component of the displacement. And you should do the sign on components before you figure out the magnitude. But now we have to figure out the magnitude of this component. So I think what a lot of people might do on this problem, some students might just kind of use this number 5 meters for the displacement or the distance that matters, but I hope that you see that this number is not the number that we need here. 5 meters is not the number we're going to plug directly into our kinematics equations, because 5 meters doesn't represent this distance, and this is the distance that the object is actually being displaced along its path. The object's not moving this way. The object is moving this way, so we need this displacement. The way to see that this is not the correct number for delta x is to remember look at the symbol here, delta x. That reminds us that delta x is measuring the displacement relative to the x-axis. Delta x represents a measurement of displacement relative to the x-axis. And again, movement in this direction is not parallel to the x-axis, but this direction is parallel to the x-axis. So that's another way to see that the correct number for our delta x relative to the x-axis is going to be the distance from here to here, not the vertical distance from here to here. But we weren't given this displacement, so what can we do? Well, I hope that when you tried the problem the first time you realized that you needed to use SOHCAHTOA. You needed to use trigonometry and SOHCAHTOA to use this number to figure out this distance. So we're going to have to kind of take a detour here and do that SOHCAHTOA. And I always recommend that you should try to keep your main sketch neat and clean. So I'm going to do the SOHCAHTOA work in a separate sketch again to try to keep this sketch neat and clean. Okay, well, in order to use SOHCAHTOA, we have to label the hypotenuse. This side is the hypotenuse. Why? Because it's opposite the 90-degree angle. Now we have to decide which angle we're going to focus on. Well, we're going to focus on this angle. We could focus on this angle at the top, but it's conventional to focus on the 35-degree angle since that's the angle that we were given. So we'll focus on this, and therefore this side is labeled as adjacent because it's adjacent to the 35-degree angle. And this leg is labeled as opposite because it's opposite to the 35-degree angle. And now we're in good shape to use SOHCAHTOA. What's our goal here? Remember, our goal is to figure out the length of this hypotenuse. We have to figure out the length of this hypotenuse because that's going to give us the delta x, and we need to know delta x because that's one of our kinematics variables. We need to know delta x so that we can put it into the kinematics framework. So we've kind of taken a detour here, and we're trying to plug the delta x into our kinematics framework. So should we use sine, cosine, or tangent? Well, we know that we want to find the hypotenuse, so that would mean we're going to use one of these two that have the hypotenuse. Tangent doesn't have the hypotenuse, and we need to use the number that we know. Well, the number that we know is for the opposite side. So we should use sine, because that will allow us to deal with the opposite and the hypotenuse. We don't want to use cosine, because that would force us to work with the adjacent side, whose length we don't know. So we're going to use sine here. And we'll say that the sine of 35 degrees is opposite over hypotenuse. By the way, what should you do if you just can't tell whether to use sine, cosine, or tangent? Well, just take a guess and try something, and if it doesn't work, try something else. If you weren't sure which of these to use first, just try one of them, and if that doesn't work, try another one. Keep trying until you get one of these three that works. Now, the length of the opposite side here is the 5 meters. And the length of the hypotenuse is what we're trying to figure out. I'm going to actually label that like this. Because remember, what we want here is the length of the hypotenuse. Lengths can never be negative. So I'm going to use the absolute value sign, so I'm using a concept that could never be negative. Now, of course, on this particular problem, we know that delta x is positive anyway, so the absolute value signs are not crucial. But I think we've seen already in earlier videos how it's helpful to use correct symbols here to remind yourself the SOHCAHTOA equations, if there were a negative sign, then SOHCAHTOA equations wouldn't show us the negative sign. So I'm going to put in these absolute values to show me that if there were a negative sign, I wouldn't figure that out from the SOHCAHTOA equations. Again, that's not too crucial on this problem because it turns out delta x is positive anyway. But it's a good habit. It's a good habit to use absolute value signs on your variables in the SOHCAHTOA equations. So I'm going to keep doing that here. Well, now we have a task to accomplish, which is that we need to solve this equation for the magnitude of delta x. Do you know how to do that? This is maybe a little bit harder algebra than the algebra that we've seen in the previous problems. Well, the first thing we have to do is get the delta x out of the bottom of this fraction. As long as the delta x is in the denominator of the fraction, we're not going to be able to solve the equation for delta x. But I think you should know how to get rid of denominators. We've seen how to get rid of the denominators on many other earlier problems, including this one. You get rid of the denominator by multiplying by a denominator. We got rid of this 78.4 denominator by multiplying by both sides of the equation by 78.4, so that's what we're going to do here. I'm going to multiply this side of the equation by the magnitude of delta x to get rid of this denominator. Now, of course, it's only legal to multiply the right side of the equation by delta x if we're also careful to multiply the left side by delta x. Let's actually make that a little bit clearer. All right, I'll write that as a separate line. so that the math is as clear as possible. And you can see that now we've accomplished our goal. We got rid of the denominator on the right-hand side. We got the delta x out of the denominator. And now, hopefully, this equation should be very easy for you to solve. We're trying to solve for the magnitude of delta x, so we have to get the magnitude of delta x by itself. So now we're going to divide both sides by the sine of 35 degrees. And we're ready to do the division. 5 divided by sine 35. Make sure you do the division in the correct order. I think a lot of students here might be inclined to do sine 35 divided by 5, but that's not right. We need to do 5 divided by sine 35 degrees. So again, write out the algebra carefully so you can see the correct order to do the division. Okay. So I'll round this value off to 8.7. Oh, here we're finding the magnitude of delta x, and that came out to be 8.7. Now that we've solved to a single number, we have some steps to take care of. We should put in the SI units. Well, the SI units for displacement are meters. So here's our magnitude of delta x. Now, remember that these absolute value signs remind us that we haven't figured out the complete delta x yet. There's a separate step where we figured out the complete delta x, including the plus or minus sign. Well, we already determined that the complete delta x would be positive. Didn't we determine that somewhere? Here I determined the complete delta x would be positive. And because the object is being displaced from here to here, and that's in our positive x direction. The object is being displaced in the positive x direction. So we can say that the complete displacement is positive 8.7 meters. Technically, this stands for the x component of the displacement, and components could theoretically be positive or negative, so we should include a plus sign when it's positive. Okay, and now we can stop to ask whether this makes sense by building this number back into our sketch. Build this number of positive 8.7 meters into our sketch. That goes here. All right, that displacement is positive 8.7 meters. And the way we can check that is remember that the hypotenuse should be the longest side of a right triangle. The hypotenuse should be the longest side of a right triangle. So we can check that because we know this side. And yep, 8.7 is bigger than 5. So we can see that we got that correct. Now notice that the correct way to do the calculation to find delta x is to divide by the sign. We had to divide by the sign to get the correct answer. But I find that a lot of students on this type of problem might multiply by the sign. A lot of students might do 5 multiplied by the sine of 35 simply because that's more similar to what we've done on previous problems. On previous problems, we usually multiplied by a sign rather than dividing. But notice that if you multiplied by the sign, you would get 2.867, and notice that then your hypotenuse would be shorter than the opposite side, and hopefully that would give you a clue that you had made a mistake. So that's a good example of the value of using this approach for checking your work. Students often on this type of problem make a mistake of multiplying rather than dividing by the sign. But if you made that mistake, you should have been able to catch it because you would get an answer of 2.86, which would imply that the hypotenuse was shorter than the leg, and we know that can't be right. So do try to be in the habit of checking that your answers are consistent with the idea that the hypotenuse is the longest side of a right triangle, and that'll give you a chance to catch your mistake if you've made one. Another mistake some people might make on this problem that maybe I already mentioned, Some people might do sine of 35 divided by 5. Notice that the correct division is 5 divided by sine of 35, but if you were sloppy in your thinking or your work here, you might get the division in the wrong direction. But notice again that you would get a number for the hypotenuse, 0.11, which is much smaller than the leg, when the hypotenuse should be longer than the leg. So we could see that either of these two mistaken approaches would give us numbers that were too small. Both of these numbers are less than 5, and so in both cases we would be able to see that we'd made a mistake. We shouldn't multiply by the sine, and we shouldn't divide into the sine. The correct approach is to divide 5 by the sine, and we see that from our algebra. And because this is the approach that gives us a hypotenuse that's longer than the leg. That's a good example of how it's useful to check your results when you're using SOHCAHTOA. It's useful to check your results when you're using SOHCAHTOA, and one way to do that is to remember the hypotenuse should be longer than the legs. All right, so now we've determined the displacement, and we can go back and put that in over here. Now, let me just pause and let me say that in my experience, students almost always get this part of the problem wrong the first time they see this type of problem. I almost never see students get this right the first time. Students almost always get the wrong value of delta x at this point for a couple of different reasons. Some students don't even realize that we need to figure out this hypotenuse. Some students just try to use the 5 meters. Some students just try to use the 5 meters as delta x. So I hope it's clear why the 5 meters here is not the displacement, because we're not moving in this direction. We're moving in this direction. Remember, this is not the final position, so we're not being displaced in this direction. We're being displaced from this initial position to this final position, and that told us that this was the direction of the displacement. That was important for figuring out this 8.7 meters. So that's an illustration of how it's useful to actually write down an I and a little f for the initial and final positions on the path. But even when students realize that this is not the displacement, most students are not able to use this to figure out the hypotenuse. Some students might not even think of using SOHCAHTOA. And if the students do, they almost always get it wrong. And the reason is that most students kind of do SOHCAHTOA on autopilot without writing out all the steps. Most students do SOHCAHTOA on autopilot without writing out all the steps. And that doesn't work when the problem is a little bit different than the ones you've seen before. How is this problem different from the ones we've seen before? Well, in the past, when we used SOHCAHTOA, I think in the past, in this video series, when we use SOHCAHTOA, we've always ended up multiplying by the sine and the cosine. Notice here that we ended up multiplying by the sine, and here we ended up multiplying by the cosine. And if you look at the previous videos, we always ended up multiplying by the sine or the cosine. So if you're on autopilot, you might assume that you should multiply by the sine here as well. But notice that no, what we actually ended up doing was dividing by the sine. And the only reason we figured that out is because we wrote out all the steps in the process. If you're on autopilot, you're not going to realize that you need to divide by the sine or the cosine here. And also, even if you realize that there's a division, you might not figure out the correct order to do the division. You might not realize if you're dividing by the sine or dividing by into the sine by the number 5. So this is a great example of the important principle of don't be on autopilot. Don't be on autopilot when you're applying SOHCAHTOA. It's really helpful to actually write out each of the steps. Now, I know that eventually you're going to get to the point where you don't want to write down every single step of SOHCAHTOA every single time. But all I can say is you have to write down enough steps so that you can tell whether this problem is similar to the ones that you've seen before. And you need to write down enough steps so that if the problem is different from the ones you've seen before, you can adapt and adjust. I hope that you realized that the geometry in this problem was this type of situation here where we had to figure out the displacement is something we haven't had to do before. We haven't had to figure out the displacement before. That should have been a sign that you'd have slowed down and written down every single step in the SOHCAHTOA here in order to figure out the correct way to do it. Most students have a really hard time applying SOHCAHTOA, and it's a little hard for me to understand why, because it doesn't seem like it's that difficult. But again, it seems to me that part of the reason is that the students are not applying SOHCAHTOA. They're just kind of doing the problems on autopilot, and that doesn't work when the problem is a little bit different from the ones they've seen before. Notice that you didn't have to kind of figure out or predict that we were going to divide by the sine of 35 in this case. We let the algebra figure it out for us. All we have to do is label the opposite, adjacent, and hypotenuse sides, use SOHCAHTOA to set up the right equation, and then we let the algebra do the thinking for us. We let the algebra do the thinking for us, and we let the algebra figure out that the calculation we had to do was 5 divided by sine of 35. Let that algebra do the thinking for you, so to speak. Don't overthink it. All right, remember again, some students might have had a little difficulty with this algebra because it was a little different from before, so study carefully if that was the case, how you did this algebra, in particular how we got rid of the denominator here, how we got the variable out of the denominator. The way to get a variable out of the denominator is to multiply both sides by that variable to cancel the denominator. So let me ask you a question. My question is, were you able to correctly figure out this displacement? If you were able to use SOHCAHTOA to correctly figure out the displacement, excellent, congratulations. That shows that you've made very good progress on understanding how to use SOHCAHTOA. On the other hand, if you were not able to use SOHCAHTOA to figure out this displacement, that means you still got some work to do to improve your skills for SOHCAHTOA. And again, my advice is, if you're in that position where you still have some work to do, keep writing out all the steps. As long as you're having trouble with SOHCAHTOA, keep writing out every single step, the way I have been. You can only start cutting corners and skipping some of the steps when you're at the point where you're always getting the SOHCAHTOA part of the problem correct. And of course, anytime the problem seems a little different from the ones you've seen before, you should be especially willing to write down all the steps to make sure that you're doing that problem correctly. Okay, now, as usual, I spent a long, leisurely amount of time describing how to figure out this delta x, but you need to keep practicing these skills until you get to the point where you can, where it doesn't take you nearly that long, obviously, to figure this out. This would only be one step of the larger problem, so you need to keep practicing those SOHCAHTOA skills until it's boringly easy for you to figure out this number, so that it doesn't actually slow you down too much when you're solving the problem. Also notice that one more thing here, it's really useful to have a very nice, clean, large sketch so that you can think clearly about the geometry here. Notice how I drew a whole separate sketch so that I wouldn't mess up my main sketch, a large, clean sketch, so I could clearly see the geometric relationships. That's also very important, especially if you're having trouble with those geometry skills. Okay, well, remember that when we left off on that detour, we were trying to fill out these variables here for the kinematics. So let's move on and deal with v initial x. Well, remember that we've decided that we're going to treat time 0 as our initial point. That should be labeled in this picture. And we're treating time 1 as our final point. So our v initial occurs at time 0. And we've already noticed that our initial velocity at time 0 is 0 because this object is starting from rest. So that's a key to getting this problem right. We have to know that this object started from rest. So v initial x will be 0. So we need to plug in 0 for v initial x. Now this is a number that some students will miss because this number 0 was not explicitly mentioned in the problem. We had to read between the lines a little bit to see that the initial velocity was 0. Remember that the wording said that the box starts sliding down the ramp, and that wording is intended to imply that the box starts sliding from rest at the beginning of the problem. If it wasn't starting from rest, then it wouldn't really be starting to slide at the beginning of the problem. It would be already sliding at the beginning of the problem. But the problem said that we started to slide at the beginning. We weren't already sliding at the beginning, and that really implies that at the beginning of the problem, the object was beginning from rest. So read the problem carefully for this type of hidden 0. Our next kinematics variable is v final x. And we've already noticed that we don't really know anything specific about the final velocity at time 1. So the best I can do with the variable v final x is to use a slightly more specific symbol and say that v final x will represent the x component of the velocity at time 1. Next, we need to deal with a sub x, and we already decided that we don't have any information yet about a sub x, so we're just going to continue to use the symbol a sub x for that, just like we did over here in our Newton's second law equation. Remember that a sub x is our connecting link. We want to use one of the frameworks to figure out a sub x and then plug that into the other framework. Now, the question is asking how long it takes the box to reach the bottom of the ramp, so we should also indicate with a question mark that this is what the question is asking us for. It's always good to build the question into the kinematic setup with a question mark. Notice that we used this idea. Since the object started at rest, its v initial x was 0. The problem implied that the object was starting at rest, so our v initial x was 0. And we've also completed this step. It's good to, when possible, build a question mark into your kinematic setup that indicates which of the kinematics variables the question is asking you for. So we did that here. On this problem, the question was asking us for this kinematics variable, delta t, and we built that into our kinematic setup with this question mark. That's a good step to complete for any problem where it's applicable. When possible, build the question into your kinematics setup, as we did here. We had already previously built the question into the sketch, but it's still also helpful, when possible, to also build the question, to also label the question in our kinematic setup. All right, now, since the question is asking us for a kinematics variable, it might be natural to start our work with the kinematics framework. But remember that in order to use a kinematics equation productively, we need to know values for 3 of the kinematics variables. 3 variables. Remember that on this problem, we're using kinematics with constant acceleration with changing velocity, so we're using this right-hand column here in the handout. So in order to use the kinematics, in order to proceed to choose a kinematics equation, we would like to know values for 3 of the kinematics variables. Well, over here it looks like we know 1 value, 2 values. We only know 2 values so far. Remember, we need to know 3 values before it's helpful to use a kinematics equation. So it looks like we're kind of stuck here on kinematics, but don't despair. We'll just try to use the Newton's second law approach. Well, remember that our plan is to use Newton's second law to find a sub x, and then we can plug that into kinematics. So now it's natural to move over to our Newton's second law x equation and try to use this equation to solve for a sub x so that we can plug that into kinematics. But are we ready to use this column? Well, count the unknowns. Notice that there are 2 unknowns still left in this left-hand column. We still don't know little n, and we still don't know a sub x. So it looks like we're not ready yet to use this left-hand column because there's still 2 unknowns. How about the middle column? Well, count the unknowns. Our middle column has only 1 unknown left. Only little n, 1 unknown left in the middle column. So it looks like our best approach is to start by solving the middle column for little n. Now, of course, little n is not what the question is asking us for, but every little thing we can figure out is going to help. If we can figure out little n, we can plug that into one of the other columns, this column, and that will make it easier for us to work with this left-hand column. To determine what order to work with the columns, focus on the knowns and the unknowns. For your left and middle columns, focus on the number of unknowns. And for the right-hand kinematics column, focus on the number of knowns. By the way, I should mention that after I recorded this video the first time, I went back and made some revisions and re-recorded a few parts of the video to try to be clearer or to use a better method. And as a result of that, there are some slight inconsistencies as you go through the video now between what's on the screen at various times. You might have already noticed that, but I hope it's nothing too major or too confusing. Well, we've decided to start with this middle column, so our next step is to actually do the algebra and solve this equation in the middle column. That turns out to be very simple, and very simple to solve algebraically. I'm adding here to cancel the negative. We've solved to a single number, so we want to make sure we put the units in. Newtons are the units for force. We should check whether this came out positive or negative and whether that made sense. Well, this number came out positive, and that makes sense because what does this symbol stand for? This symbol does not stand for the normal force. This symbol stands for the magnitude of the normal force, and magnitudes have to be positive. If this result had come out to be negative, we would know we'd made a mistake because magnitudes can't be negative. Let's actually pause and ask if the size of this result makes sense. If you haven't done so yet, pause the video and ask if the size of this result makes sense. Well, let's compare this to the weight, and we can see that the magnitude of the normal force came out to be less than the magnitude of the weight. Let's see why that makes sense. Well, remember from our forces handout that the purpose, so to speak, of the normal force is to prevent an object from moving through a solid surface, like the surface of this ramp. So the magnitude of the normal force will be whatever it takes to prevent the object from moving through the surface of the ramp. Well, in this problem, who is trying to move this object through the ramp? It is W sub y. The y component of the weight is trying to drag this object in this direction into the surface of the ramp. The y component of the weight is trying to pull the object in this direction into the surface of the ramp. So the important point there is that notice that only the y component is trying to drag the object through the surface of the ramp. The x component of the weight is pulling the object parallel to the ramp, not into the ramp. So that shows us that the normal force does not have to cancel out the entire weight in order to prevent the object from beginning to move through the surface. The normal force only has to cancel the y component of the weight. We can see that from this diagram. This is a free body diagram where I'm showing all the components of the forces. In this free body diagram, I've broken the weight force into components. Remember that we figured out earlier that the components of the weight force are pointing down and to the right and down and to the left. So here I showed the components of the weight force pointing down and to the right and down and to the left. So from this diagram, we can see that the normal force only has to cancel the y component of the weight, while a component of a force is generally going to be less than the overall force. So it makes sense that the magnitude of the normal force came out to be less than the magnitude of the weight, because the normal force only has to cancel out one component of the weight on this problem rather than the full weight. If the normal force had come out to be greater than 78.4 newtons, hopefully we would realize that we had made a mistake. I believe that in the previous two problems in this video series, the magnitude of the normal force came out to equal the magnitude of the weight. But I hope that didn't make you think that you should always assume that the magnitude of the normal force equals the magnitude of the weight. Sometimes the normal force and the weight are equal in magnitude, such as in those two previous problems in this series. But oftentimes, the normal force and the weight are not equal in magnitude, such as on this problem. So don't make an assumption, just use the Newton's second law equations to determine what n looks like for the particular problem that you're working on. All right, so we've checked that this result makes sense. Now what? Well, now we have to take this value for little n and substitute it into one of the other columns. Well, little n does not appear in the right-hand kinematics column. Little n does appear in this left-hand Newton's second law x column, so we need to make a substitution. Let's substitute little n into this column. And notice now we have one unknown in this equation. There's now only one unknown in this equation, which means now is a good time to try to solve this equation for a sub x. Now we could do the simplify the left-hand side in one step on our calculator, but I'm actually going to split it up into two steps just because I think that'll give us more insight. This will give us more insight into the relationship between the forces if we split this up into separate steps. So now we can do 45 minus 19.26. Oops. So we get 25.74 equals 8ax. This equation should now be easy to solve. .74 divided by 8. I'll round that off to 3.2. I guess I'll use keep in another digit here, just because that feels comfortable here. This is a 7, so this turns into a 2. I'm just trying to keep enough digits to make it as convenient as possible for people to check their answers and make sure they're getting the same answers as I am. So that's our result. Now that we've solved to a single number, there's some steps we have to take. We have to put in the SI units. Well, the SI units for acceleration are meters per second squared. And we should ask whether this makes sense. Well, we can ask whether the plus or minus makes sense. So mathematically, this came out to be positive. This came out to be positive mathematically. Does that make sense? How do we decide whether it makes sense that the acceleration is positive? Well, let's try building that acceleration vector into our sketch. So I can do that here. Notice I've drawn the acceleration pointing in the positive x direction. I've drawn the acceleration pointing in the positive x direction, which is consistent with this positive value. Remember that we've already decided that the y component of the acceleration is 0. Since the y component of the acceleration is 0, the overall acceleration vector points in the same direction as a sub x, and that's the positive direction here. Now let's ask if that makes sense. Do these velocity and acceleration vectors make sense? So what does this velocity and this acceleration mean? Well, the direction of the velocity indicates the object's direction of motion, so we know that we're moving down the inclined plane. And because the acceleration is parallel to the velocity, the object will be moving down the plane with increasing speed. We can say something extra though here. Remember, we know that the object started from rest. Remember that actually at time 0, the velocity is actually 0. At time 0, the velocity is 0. It's only after time 0 that the velocity is pointing down the inclined plane. This arrow only applies to the times after time 0. This arrow only applies to the times after time 0. At time 0, the velocity would have would be 0 and have no arrow. So what we can actually say is that this object is starting from rest, then moving down the inclined plane with increasing speed. We know we began from rest because that was implied by the wording of the problem. So it's implied that v initial is 0. The box then is moving down the ramp. That's reflected in this downward velocity, and that was also stated in the problem. And our acceleration came out to be parallel to that velocity. Well, remember that when the acceleration is parallel to the velocity, that means the object is moving with increasing speed. So it does make sense that the acceleration is in that direction. So it makes sense that the acceleration is pointing in this direction so that the object can move down the ramp with increasing speed. Now, we've talked about how the acceleration vector does not indicate the object's direction of motion. But actually, that's a little bit of an oversimplification. The complete statement is that by itself, the direction of the acceleration vector does not indicate the object's direction of motion. But if you combine the acceleration vector with other information, sometimes that will tell you what direction the object is moving. That's something we haven't talked about before, but now we can talk about it. By itself, knowing the acceleration vector would not tell you the object's direction of motion. But if you also know that the object starts from rest, then the direction of the acceleration does indicate what direction the object will begin moving. Once an object is moving, the acceleration doesn't tell you what direction it's moving. But if an object starts from rest, then the direction of the acceleration will tell you what direction the object will begin moving. So again, it makes sense here that the acceleration is pointing down the inclined plane, because that's necessary in order for the object to begin moving down the inclined plane. Remember, the object started from rest, so we need this downward acceleration in order for the object to start moving down the inclined plane. Acceleration causes changes in velocity. Well, the velocity started at 0, but we wanted it to change to start pointing down the inclined plane, so we needed an acceleration to cause that change down the inclined plane. Suppose that instead of this acceleration, suppose that the acceleration was just 0. Well, do you see how that would clearly be wrong? If we started at rest and the acceleration was 0, wouldn't we just stay at rest? That's not consistent with the information in the problem. So clearly a 0 acceleration wouldn't make sense, because if the object started at rest, a 0 acceleration would just keep it at rest. So clearly that would be wrong. And do you see how obviously a negative acceleration would also clearly be wrong? If the object started at rest and the acceleration was pulling in this direction, then the object would actually start moving in this direction. Remember that by itself, the acceleration doesn't show you which way the object will move. But if you know the object starts from rest, then the direction of the acceleration vector does indicate what direction the object will begin moving. Well, if this object had started with a velocity of 0 at rest, and then it had a negative acceleration, that negative acceleration would have pulled the velocity in this direction and have started the object sliding up the plane, which obviously is not consistent with the information in the problem. So it definitely would not have made sense for a sub x to come out to be negative or 0 on this problem. So a positive acceleration makes good sense. I know that's not necessarily very easy analysis. We've started complicating our analysis of the acceleration here. I used to just tell you that the acceleration does not indicate the object's direction of motion, but now we have to see it's a little bit more complicated than that. By itself, knowing the acceleration does not indicate the object's direction of motion. But if you know that the object is starting from rest, then the direction of the acceleration vector at that time does indicate what direction the object will begin moving at that time. Acceleration is one of the most difficult and subtle concepts in physics, so it shouldn't surprise us that we're starting to get a more difficult and subtle understanding here of how to interpret the acceleration. Overall, though, I think that this positive acceleration should make sense. I think this really matches our common sense. Our common sense for what would happen in this situation is that the box starts from rest, and then the object will begin sliding down the inclined plane, and it's going to move with steadily increasing speed. So that positive acceleration makes sense. Remember that it's a good idea to put a plus sign in front of positive components. So I'm going to go ahead and put a plus sign in front of this positive component to emphasize that it's positive and that that makes sense. By the way, remember that earlier we decided that on this problem we were going to apply the form of kinematics that involves constant acceleration. And we said that we knew that the acceleration would be constant because the net force on the object is constant. And we knew that the net force would be constant because the individual forces would be constant. So earlier in our analysis, we said that it looked like the forces would be constant in this problem. And now we can confirm that that's really true. Certainly the weight is constant in this problem at 78.4 newtons. And then we discovered that in magnitude. And then we discovered that the normal force would be constant at 64.2 newtons. Notice that we got a single number for the magnitude of the normal force with no indication that this number would be different at different points in time. So this result implies that the normal force is constant in magnitude at this value. And then later we discovered that the frictional force would also be constant. Here we discovered that the frictional force is going to be constant in magnitude at 19.26 newtons. And again, this is a single number with no indication that this number is going to be changing at different points in time. We've now derived a single number for the magnitude of each of the three forces in this problem at every point in time that we're considering in this problem. And that confirms that the forces really are constant in this problem. So our initial analysis that the forces in this problem would be constant has been confirmed by our results. That confirms that the net force is constant, and that confirms that the acceleration is constant. Of course, we know the velocity is changing, so that confirms that we're using the correct kinematics approach. We've confirmed that it's correct to apply a kinematics approach that involves constant acceleration to this problem, because we know that the forces are constant. When the net force in an object is constant, that's when you can conclude that the acceleration is constant. That was a detour to check if this answer makes sense, and now we want to continue. Remember, we still have to figure out this answer, delta t. So our goal now is to plug that and substitute a sub x into our kinematics framework. Sorry, I can't resist. Sorry, I can't resist. There's one more thing we should check here to see if a sub x makes sense. Obviously, if you're not interested in the discussion, sorry about that. You can just kind of skip ahead to the next part of the solution. But for those who want to build their physics insight, sorry, I got to go over one more thing here to help us understand a sub x. Does the size of this answer make sense? Does the size of this answer make sense? What could we compare this to see if it makes sense? Well, we could compare this to little g. Free fall acceleration, the acceleration just due to the force of the Earth's gravity. So you can see here that we got that a sub x came out to be less than little g. Little g is a magnitude, so to make it a fair comparison, we should focus on the magnitude of a sub x. Well, this is smaller than little g. Does that make sense? Does it make sense that we're accelerating at less than free fall acceleration? Does it make sense that we're accelerating at less than free fall acceleration? I hope you gave that some thought. Well, first of all, it just makes sense in terms of common sense, right? I think your common sense would tell you, even if you'd never studied physics, I think common sense would tell you that if you dropped one box from here and you let another box slide down an incline, I think common sense would tell you that the dropped box in free fall would accelerate faster than the sliding box, even if you haven't studied physics. But why does this make sense in terms of physics? Well, remember, what does little g stand for? Little g is the magnitude of the acceleration that would be caused by the full weight force. Remember that little g is the magnitude of the acceleration for projectile motion when the only force on the object is the force of the Earth's gravity. Little g is the magnitude of the acceleration when the only force on the object is the weight force. But on this problem, the magnitude of a sub x, that represents the magnitude of the acceleration on this problem. Well, this acceleration on this problem is not being caused by the full weight force. A sub x on this problem is only being caused by w sub x. It's only being caused by one component of the weight force. So since a sub x is being caused only by a component of the weight force, that by itself would explain why a sub x should be, on this problem, would be less than the little g value that would apply to free fall. A component of the weight is always going to be less than the full weight when both of the components are non-zero. So a sub x is less than the free fall acceleration because a sub x in this problem is only being caused by a component of the weight. And furthermore, we know that w sub x on this problem is being partially canceled by the friction. Since the weight force is being partially canceled by the friction, that gives us a second reason why the magnitude of the acceleration on this problem would be less than the magnitude of the acceleration in free fall. In free fall, the acceleration is caused by the full weight force, not canceled out by anything else. But on this problem, a sub x is being caused only by one component of the weight force, which furthermore is being partially canceled by friction. So for those two reasons, it makes good sense that the magnitude of the acceleration on this problem is less than the magnitude of the acceleration would be in free fall. So if a sub x had come out to be bigger than 9.8 meters per second squared on this problem, I hope you would have realized that you had made a mistake. Okay, so this analysis gives us another way to check that our answer makes sense, and I hope that this analysis also, again, helps you to get a deeper insight into the physics behind this problem. I know that this type of analysis is challenging and can be difficult, but the more you practice thinking through these issues, the less difficult, hopefully, it'll become. Okay, sorry about that. But now we can go back to our solution. I guess I feel free to take those detours in these solutions because, like I said, if you're not interested, I hope that you'll just be willing to just kind of skip ahead in the video and find the next part of the video that is of interest to you. And of course, always keep in mind there's complete written solutions to all of these problems. And you can rely more on those, again, if you find the videos are going too slowly or dealing with topics that you're not interested in. Okay, so let's see here. Now we have a sub x, and we're going to substitute that into our kinematics framework. Actually, I'll keep this and make this substitution. There we go. So we can build this in. This is now, we know, positive 3.22 meters per second squared. All right, so now notice that there are three knowns. There are now three knowns in our kinematics framework. But when you know values for three variables, that's when you're ready to choose a kinematics equation. So we're ready now to choose a kinematics equation. And we're going to do that by asking which variable do we not care about. Well, clearly we care about the three knowns, and we clearly care about delta t because we need to solve for that variable. So the thing that we don't care about is v final x. We don't care about v final x on this problem because we don't know a number for it and we're not being asked about it. So let's pick the equation that's missing v final x. Let's pick the kinematics equation that's missing v final x. Here it is. Here's the kinematics equation that is missing v final x. Remember that we want to choose from this box of equations because this is the box for that contains the kinematics equations that apply to constant acceleration with changing velocity. And we're choosing from the x component equations on this problem because the object is moving in the x component. So we'd like to write out this kinematics equation now. On this problem, the kinematics variable that we don't care about is v final x. This is the kinematics equation that's missing v final x. So this is the kinematics equation that we're going to work with for this problem. So the equation that we're going to use here is delta x equals v initial x delta t plus 1/2 a sub x delta t squared. Remember to write the general equation before you start plugging in. So now we can plug in 8.7. I'll leave out the plus sign now just to make the math in the equation easier. 0. And let me just point out here a couple of things. So again, this key number here, 8.7, remember this is the number we figured out from SOHCAHTOA. We needed to get this number of 8.7 from SOHCAHTOA. That's what we did over here to figure out that 8.7. And this number of 0 we figured out because it's implied by the wording of the problem that the object began at rest. So we had to do a little work to get these two numbers. Suppose you hadn't gotten these two numbers. Well, if you hadn't gotten these two numbers, hopefully you would realize you were missing something, because then you would only have one known, and you wouldn't be able to proceed with kinematics. So if you don't have enough numbers that you know in your kinematics framework, even after you've already done as much as you can with Newton's second law, that's a clue that you need to work harder to figure out more of the variables. So some students at this point might have only known the acceleration from Newton's second law, and hopefully they would see then that they don't have enough information for the kinematics equations, and hopefully if they thought about the problem more carefully, they would then see that they can put in a 0 for v initial x by supposing that the object starts from rest. That's implied by the wording, and hopefully you would see that to get the third known that you need, you could use geometry. You could use SOHCAHTOA and geometry to figure out the length of the hypotenuse of this ramp. Okay, so those were important numbers. Now here we have our delta t, which we don't know, so I'll keep writing it as delta t. A sub x is our 3.22. And again, as usual, when we write numbers by themselves, I include units, and for components I include a plus or minus sign. But when I plug into the equation to make the math simpler, I leave out the units and I leave out the plus sign. And here's our delta t. Don't forget to square that. Now we can start simplifying. So we need to do the calculation 1/2 times 3.22. So our new equation is 8.7 equals 1.61 delta t squared. Oh, I forgot to mention, did you notice that the kinematics equation we used on this problem is different from the kinematics equation that we used on the previous two problems? On the previous two problems, I believe we used this kinematics equation. But now on this problem, we're using this one. Anyway, that's just another good illustration of why it's important to not be on autopilot. Don't be on autopilot. Just because we've used this kinematics equation a couple of times doesn't mean we should forget about the other two equations. So again, don't be on autopilot. Instead, follow the process. Set up your kinematics framework, and when you know 3 variables, ask which variable you don't care about and use that to pick the equation, because you might need a different equation on different problems. So this is a kinematics equation that we haven't had an occasion to use yet in this video series until now. Okay, now to continue solving here, it looks like we need to get the delta t squared by itself. So we need to divide both sides by 1.61. So we have the division 8.7 divided by 1.61. So I'll round that off to, I'll round that off to 5.4. Okay, because this side is being squared, I think you know that we can then say that delta t is the square root of 5.4. Since delta t squared equals 5.4, that means that delta t is the square root of 5.4. A little complication, remember that every number actually has two square roots, a positive square root and a negative square root. So anytime you take a square root, you want to ask whether you want the positive or the negative square root. Well, I think that should be pretty obvious here. We're trying to figure out time elapsed, and time elapsed can never be negative. So we want the positive square root, and that's actually what this symbol means by itself. This symbol means the negative square root, and the radical symbol by itself already means the positive square root. So I don't need a plus sign here. The symbol by radical by itself means the positive square root. All right. You might think that I'm being over careful about that, but there are other times in physics where you have to use the negative square root. There are times in your physics class where you have to take the negative square root. So you need to get into this habit, even though it's pretty obvious in this case. When you take a square root, you always have to ask whether you want the positive or the negative square root, because there will be some problems where it's the negative square root that you need. But here what we want is the positive square root, so we can get a positive time elapsed. So now we can do that calculation, the square root of 5.4. Okay, and so we've gotten that our delta t is I'll just round that off to 2.3 now, 2.3. Remember that now that we have a single number, we should put in the units. So I'll put in the units here of seconds. Does this result make sense? Well, obviously it makes sense that it came out to be positive because we just forced it to come out to be positive by taking the positive square root. Can we ask whether the sign of this answer, whether the size of this answer makes sense? Does the size of that answer make sense? Well, just think about the common sense of what's happening here. We're starting from a height of 5 meters and sliding down a ramp from a height of 5 meters and an angle of 35 degrees. So if you're not familiar with meters in everyday life, keep in mind that a meter is about a yard. So this is about 5 yards, a height of 5 yards, which you, so if you're from the US, you might not use meters too much in everyday life, but you should be familiar with yards because of the yards on a football field. So you should have a vague idea of how long 5 yards is from a football field. So this is at a height of 5 yards. So does it make sense? By the way, also remember that a yard is 3 feet. So this is also about 15 feet. So it's sliding from a height of about 15 feet. Does it make sense that it could reach the bottom of that hill in about 2 seconds? I think that's about right. That seems about right. It doesn't seem too bad. Suppose that we had gotten an answer of 0.2 seconds. That might seem really alarmingly fast. Can it really slide down from a height of 15 feet in 0.2 of a second? I'd be pretty suspicious of that. And if you got this, that would seem way too small. And on the other hand, suppose it came out to be 23 seconds. That might start to seem suspiciously slow. Maybe not for sure. This would be pretty slow. But of course, suppose you got 230 seconds. 230 seconds, that's more than 3 minutes. Well, more than 3 minutes, I think we'd be very suspicious of this answer and think that it was very likely. This isn't impossible, but it would seem suspiciously large, and we'd start to think that maybe we'd made a mistake. Okay. So based on our common sense for the situation, 2 seconds seems to be at about the right range for judging this. Now keep in mind that when you're trying to ask if your answers make sense, sometimes if you're from the US, it can be difficult to think about that because we're not used to using the metric system in everyday life. So keep in mind that a meter is about a yard. You know about how long a yard is from a yard on a football field, perhaps. And also keep in mind that a yard is 3 feet, and that can help you to get a better intuitive sense for what the distances in the problem mean if you're not used to using the metric system in your everyday life. In most other countries, people actually do use meters commonly in everyday life, and in that case, you'd have an advantage for thinking about the common sense of our results that come out in the metric system. When you're checking whether your results make sense, it helps to build the results into your sketch. So I built the 2.3 seconds into the sketch, and that reminds us that what we're saying is that it takes 2.3 seconds to slide down this inclined plane from a height of 5 meters. So by building this number into the sketch, that helps to remind you of the common sense of how we're going to be interpreting this number. And again, I think this number does make sense in this situation. So it's a good idea to try to build your results back into your sketch. That helps you to remember what the significance and meaning of the results is in the context of the problem, and also helps you to see whether the answers make sense. Okay, so I've gone ahead and written the answer to the question here. So we can make sure that we've done our last step. Remember that at the end of the problem, you want to check that you answered the right question and that you answered all parts of the question. So for example, this question could have asked you, say, how quickly is the box moving at the bottom of the ramp? So make sure we answered the right question. It's not asking that, it's asking how long it takes. And are there any other parts of the question? Well, no, not in this case. We've already checked that our answers and also our intermediate results made sense. Make sure you include units. If you leave out the units, your answer is wrong. It would be a shame to lose credit after all that great work we've done on this problem just because we left out the units at the end. And of course, our answer is numeric, so this step for symbolic answers does not apply. Okay, all right. So now it's time to review what we could learn from this problem. Here is a summary of some of the key work that we carried out for solving this problem, and a reminder of how we used the free body diagram, force table, and then the 3-column approach for organizing our math. The biggest new issue on this problem was getting this number. So you should pause and make sure you understand how we got this number, positive 8.7 meters for delta x. Remember, we had to apply SOHCAHTOA in a somewhat novel way to obtain this number, 8.7 meters for delta x. Remember again, try to model your scratch work on the scratch work that I used on this problem. These problems are now getting longer and more complicated, and so it's really important to keep neat, clean scratch work, or you're going to get really confused as you're working through the problem. So try to keep your scratch work at least as neat and clean as I am. So remember, don't try to put too much stuff in one sketch. Here was our main sketch, but we did the free body diagram in a separate sketch. And then when we were breaking the weight into components, we did that in a separate sketch. And even when we had to figure out this hypotenuse, I even did that in a separate sketch, just to keep each sketch as neat and clean as possible. Now I know when you take your exam, you might have some limits on how much scratch paper you have. There might be limits on your scratch paper when you take the exam. And there's also limits on your time, but all I can say is to the extent that your time and your scratch paper allows, draw large, neat sketches and draw multiple sketches so that the sketches are not getting too messy by having too many different pieces of information in them. And I would certainly recommend whatever you're going to do on the real exam, right now, as a beginner, when you're first learning how to solve these problems, now that you're first learning how to solve these problems, if you're finding the problems to be difficult, use lots of scratch paper and draw multiple sketches. Don't try to put a lot of information into one sketch, or the sketch will get too confusing. So when you're first learning, be willing to use lots of scratch paper, even if you won't have that much paper available on the real exam. That's the way to build your skills. Remember, we want to have a neat, clean, free body diagram and a neat, clean force table. You should be modeling your scratch work. Hopefully will look a lot like what I have here on my screen. And then notice how I tried to keep the math organized by organizing the math into 3 columns. So if you can fit it on your paper, have one column for the x component for Newton's second law, one column for the y component for Newton's second law, and then if you can fit that in, one component for your kinematics framework. And that makes it, I think, a lot clearer to not get confused and to see the substitutions that you need to make. We used this equation to find n. We substituted that in over here. Then we used this equation to find a sub x and substituted that in over here. So notice that we executed our plan in this case. We figured out a sub x from Newton's second law, and then we substituted that into kinematics. A sub x was the link, just as we had expected as we were solving the problem. But besides figuring out a sub x, we had to figure out also the normal force from the y version of Newton's second law. in order to plug that into the x equation. Remember that that's very typical when you're solving friction problems. When you're solving friction problems, it's very typical to first have to figure out the magnitude of the normal force from the y version of Newton's second law, and then plug that into the x version of Newton's second law, because that also involves the normal force, because remember, oftentimes the formula for the magnitude of kinetic friction involves the normal force. So on friction problems, we generally first have to find the magnitude of the normal force before we can work further with these friction equation over here. I continue to really encourage you to use this framework for kinematics. Write down the general symbols for the 5 kinematics variables. Then write down the specific numbers or symbols that you're using for that problem. This is the way to stay organized and avoid getting confused when we're juggling a lot of different pieces of information involving kinematics. We don't know which kinematics equation we're going to use from the beginning, so we can't just start with an equation like we did here and here. Here we started with equations, but we can't start with an equation for kinematics because we don't know which equation we're going to use. So instead we start by listing the variables. That's the way, and then listing the data that we know about the variables. That's the way to stay organized. What were the new complications on this problem? Well, we've already done inclined plane problems in the past, and we've already done friction and kinematics problems in the past, but we've never combined all 3 of those into one problem. This is the first problem where we had an inclined plane and friction and kinematics. So you can see the difficulty level of these problems is ramping up, no pun intended. But as we ramp up that difficulty level, I hope you can see that we're not winging it. We're going to continue to use the same overall process. I hope that you can see that we really are using the same kinematics process on each problem, and that we really are using the same Newton's second law process on each problem, even as the difficulty of the problems ramps up. We're not winging it. Now, the other thing that was new here is that we had to do some extra separate geometry to find the length of the ramp. We had to do some separate geometry to find the length of the ramp. That's something we haven't had to do on any of the previous problems. So this was the part of the problem where it was important that we not be on autopilot, and we needed to adapt to the new needs that we had for this new problem of finding this length. And again, the key for getting this right is being willing to write out to make a nice clean sketch, make a nice clean large sketch of the situation, and then to be willing to write out all the steps of applying SOHCAHTOA. If you write out all the steps, SOHCAHTOA should not be that difficult. SOHCAHTOA is only difficult when people try to skip steps and figure out the result on autopilot. So that was one of the key issues that was new here. The professor doesn't think this part of the problem is hard. The professor thinks this part of the problem is easy, so you need to practice till you get to the point where this part of the problem is easy. I think most students would get this problem wrong. And one reason that people get this wrong is they misuse this number of 5 meters. As I've already mentioned, a lot of students would take this number of 5 meters and they would try to plug that in for the displacement. A lot of students try to take this number of 5 meters and plug it in for the displacement. Do you see why that's tempting? It's tempting because it has the right units. We do want a number in terms of meters for the displacement. So it's tempting to take this 5 meters and plug that in. But we saw that that doesn't make sense. From our sketch, we can see that the displacement is this distance, not the 5 meters distance. So the moral of that trap, to avoid that trap, you need to understand this idea. Don't assume that the number you're given in the problem is the number you need to plug into your equations. We were given the number 5 meters in the problem, and that has the right units for delta x. But we don't want to plug in 5 meters for delta x. It would be a mistake to plug in 5 meters for delta x in our kinematics equation, even though it has the right units. That's one of the traps in this problem. The professor has set up a trap here where they gave you a number with the correct units, hoping that you would kind of be on autopilot and plug it in for delta x without realizing that this is a distance, but it's not the distance that we need. So watch out. Please recognize that that's a common trap on physics exams. A common trap is to give you a number that has the correct units to be plugged into an equation in a certain spot, but it's still not the right number to plug into that spot. Just because a number has the right units, don't assume that that's the number you need to plug into your equation. Now, of course, that certainly doesn't mean that we ignore the 5 meters. Obviously, we did not ignore the 5 meters, but we used the 5 meters to figure out the number that we did need. We used the 5 meters to figure out the number of 8.7 meters that we did need to plug in, and then it was that 8.7 meters that we actually plugged in for delta x. So be aware that this is a common trap and start trying to get into the habit of watching out for this trap when you're doing physics problems. So here's a more explicit way of writing that out, including the fact that even if a number has the right units, it might not be the right number to plug into your equations. Now, of course, some numbers are the correct numbers to plug into your equations. This number has the correct units for mass, and if you think about it, this is the correct number to plug in for the mass of the box. So we're just saying don't assume, think about it. Think about whether each number is the right number to plug in for a particular variable. So you want to pay attention to the units, but don't assume that because something has the right units, it's the right number to plug in. You have to think about it. You have to think about the details for each number to see whether it really makes sense to plug it in for a particular variable in a particular equation. So that takes practice. And again, I'll just remind you one more time, the way that we saw that this distance is not delta x and this distance is delta x, part of that was by labeling the initial and final points on the path. The object is being displaced between this initial point and this final point. That's how we knew that this was the displacement. So that's just another good argument for using the notation that we've been using in these videos. Draw the actual path of the object. Here we drew the label the actual path of the object, and we labeled the initial and final points in that path, and that will hopefully help you to see clearly that this distance represents the displacement and not this distance. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.